Hello boys and girls. In this video we're going to discuss the category theoretical definition and characterization of the dependent product or the dependent product functor really. That's the same dependent product that gives dependent type theory its name. Although whenever you're in a concrete situation, of course, whenever you deal with a concrete category, and especially if it's sets or types, then you get these instances of the concept in simpler terms, of course, but nonetheless we're going to discuss the abstract error theoretical characterization in terms of adjoint functors really, and start with the set theoretical one, which is quite graphical. And sorry for the cheap quality and setup here. I needed to draw diagrams and didn't want to do it in LaTeX, and I didn't get the better camera out, but I guess it will do for this video. So let's get into it. Firstly, I will describe the situation as we have it in set and then generalize from that. So we have some functions, for example, from x to y. In general, this will then be errors. I will in this video denote the classes of errors by C for the category and then this bracket. So C x to y would be the class of errors from x to y. And in sets, these objects have an internal representation. There y to the x is the notation in terms of cardinalities. Also, if you read the spaces as sets without any other restrictions, but just considering the functions, then you write y to the power of x. And so if you have the simple case of functions, then you can represent the functions also as graphs. So here I have the x-axis and then y, and let's say this is x and this is y, and I have written down some silly example. So some function f that goes from the reals, x is the reals, to the set y is this interval from -3 to 3, and this function is given by 3 times sinus of x. And so we have this, in this picture, we have this box here, which is just the Cartesian product of x and y, as sets x and y and x are like whether you take the product like this or like this. This is the same thing as they are in bijection, and I call this product E. And one thing which will be important later, we can also characterize these functions not just as functions from x to y, but also functions from x to E, like functions from x to the Cartesian product of y and x, if we promise to actually not do anything with the second component, right? So here's this condition that this pi r is the projection to the right component. So this maps whatever pair you have with y and x just to x. If whatever you get from f that goes to E is projected back to x, so if you leave the second component to identity, then this space of functions is also in bijection with the functions from x to y, right? So make sure that you get that before you go on. So the only thing I do here is I change the codomain by adding this x again, but I do nothing with this second component. I just project the x to this extra x. Okay, and so if we go now to the dependent situation, this is more interesting. So dependent functions, if you model them like in terms of sets, are similar to the functions, except they are not really functions. What happens here is that for every value x that you could have, the codomain, like where the function maps into, is given the possibility to be different. So for any value x here, this y could be some different codomain, you can say. And so how would we model that in terms of sets? Well, I have here a function small y that maps from x to some universe of sets, like there's some selection of sets that we might take into account. So this small y picks out different set for each x. So here for x3, for example, you have y from x3, this is like one set, and for some other x you would have another set. The set is the bar basically. And now if we talk about functions in this generalized graph setup, then that would also be some line that goes through it, but it's a little bit more difficult given that the codomain is different for every value. So it's a dependent function, right? The codomain varies with the input. So if we would want to talk about a function space, we could do something like that. What we cannot do is just take the disjoint sum of all these lines. We cannot take the disjoint sum over the y of x's, because we would, to have something like a function, or we'll call it section, we have still to make sure that over every x there's actually a value being taken in the set over it, right? So what should not happen is that like if we would not be careful and we would say we define some function s that for x1, for example, maps to a value that is in this set or in this fiber over y of x3, then in that case that would not like make for something which looks anything like a function, because no value is taken. So we still have to make sure that the graph hovers over the domain x in this way. And so how do we force this condition? Well, the first observation is that if this small y selects sets that are that can be distinguished, so like this is automatically the case. For example, if we look at types, and we have different types and the elements all have their own type, then we can talk about these fibers, like these sets over each value x of like x0 in this case, as the inverse image of this function y for the particular value. And for any value that is in this inverse image, so for example, if here we have a value here, let's call it v, then we can project it back to the domain, right? So there's some sort of projection function which is similar to what we had with this literal right projection here, that would map it back. So using this kind of projection, the projection is just a function which maps from the fiber into the base, we can characterize the sections as the functions that go from x to the disjoint sum of the y of x's, but with the extra condition that the p, like if we apply this s and go from the domain into one of the fiber and then project it back, then we should come back to this the place that we were before. So p concatenated with s, or s concatenated with p, should be the identity. So this is a way to characterize this sort of function space, right? And this function space is going to be the dependent function type, the dependent product. So let's make some observation about this dependent product in, like as I have now described it, in the world of sets. First thing, if we look at this disjoint sum, and let's say that like all the sets involved here are just finite sets for the sake of it now. So x is a finite set, and each fiber y of x is also a finite set. Then if we look at the cardinality of this graph, like of this of the graph, basically of the space in which a graph is drawn, like if we sum together how many elements, how many possible different values are there, And since it's a distinct sum, we can basically imagine that as just counting all values here, and summing them up. Then we figure out that the dependent sum over y of x is actually just the sum of the cardinalities of this y of x's. So in that sense, the dependent sum translates also to a literal sum of the cardinalities. There's this simple relation between cardinalities. And it's also clear if all these fibers are finite, that the cardinality of the dependent product will actually be the normal product of natural numbers of the cardinality of these fibers. Because, I mean, you can think about it, if you want to count the functions that are possible in the space, and you can say, well, for the value x0, so and so many values can be taken. And if you speak of one function and you take one value, and then you go to the value x1, so and so many functions can be taken. And if you have no restrictions about like continuity or anything like that, if you just consider the function as we do here, the sections really, then the number of possible sections there are is just a product. Like this is, like, you can think about it combinatorically. So this is more or less just to justify why we would call it even a product, because it literally translates with the cardinalities as you would expect. And also, just as a side note, if we go back and say all our y's are actually the same y, so over every value x, small x, there is the same fiber, except we maybe tag it which fiber it is, but it's the same set as a set. Then, so this is this condition, if for all x, this y of x is just some constant set, then the dependent product over the y's is just, you know, 1 for every x. Then we get back just y times x. So this is exactly the situation that we have here. So this the dependent product, this disjoint sum over y's would be e. And similarly, if this condition holds, then the dependent product also reduces to the function space, also in terms of cardinalities, right? Because now we have, you know, the cardinality of one y times the cardinality of the next y, and so on and so forth. Okay, so far so good for the set theoretical case. And now let's introduce a few concepts. If you know category theory already, then you might be able to skip the next 3 minutes. But what we're going to need is firstly the idea of a slice category. Then let's say the pullback, or at least the product of objects in a category. So we're talking about Cartesian closed categories here. So we have always, for every objects exists a product like it did with the sets. And then also need to talk about joint functors very quickly. Okay, so first thing, the slice category of an object. So if you have some category C and some object X, then you can consider, like, for some given object X that lies in the category, you can consider all the functions in the whole category that in one way or another like map into X, and that would be the example in sets where we speak about functions. If we speak about general categories, then it's just basically the collection of all errors. And you might want to look up the definition. You can also speak of then errors between these errors. Basically, this is like you know, what's the English word? Like whenever you can concatenate two functions to extend it to another function, then the codomain will not change, and that's the way in which you can define also errors of these errors. But okay, that's not so important for this video. The main idea here is just that it's kind of intuitive that we can go from the category to the category in which the new objects are just functions into one particular object. And also in this type of categories, if this category has a terminal object, so if this category has an object into where for each other object there's only one object into it. So the example in the category of sets would be just an object with one element, so a singleton. Right? For every function, like for every set, let's call it B, there's only one function from the set B to a singleton set, namely the one that takes any element of B and maps it to the same single object. There's no other options. So I denote it with a star here. There's a conventional way of denoting this terminal objects, and the morphisms into it, the errors into it, are called terminal morphisms. And this, you can identify this category over, like this last category, over this terminal object actually with the category itself, because basically for each object you only have one error into this terminal object, and so there's a 1-1 correspondence. In terms of functions and sets, that would be just taking a function and considering its domain. Right? If you have a function from B to this terminal singleton object, then taking the domain of this function gives me set B, so there's this 1-1 correspondence. Okay, and the other notion that we will need is the pullback. We don't need many technicalities in this video actually about it, but the idea is that if you have given two errors, alpha and beta here, which map to the same object V, then you can ask whether or not you can like do the pullback of one object, like one error with respect to the other. So in essence, this is like taking this B, this beta, and pulling it along alpha to get another error here. And there's then some technical conditions where you say I define this pullback of beta along alpha in such and such way that this not only does this square commute, like these new functions that are obtained this way should like fulfill this the relation that is given by this commuting triangle, but in a certain sense these functions and this object which is created in this way is also the optimal or minimal object. Okay, so this is if this is speaking about pulling back errors along each other. So here beta is pulled back along alpha, and the nasty diagram that we will talk about and in the rest of this video is going to be this here. So I will just go through the items. The main important thing here is the square in the middle, and the parts on the right will then be more clear when I go to the adjoints. So here we have some object A, then a terminal object. So this is a Cartesian closed category where we have this terminal object. There is exactly one error from any object that lies in the category to this, and this is denoted with this bang. You know, bang A is this terminal morphism that goes from A to the terminal object, and then there's bang X. You know, these two. And if you do if you pull back the bang A along bang X, then you get some object which makes this square commute, and this in this case happens to be just the product which is defined in a Cartesian closed category for all objects. So this is the way of characterizing the Cartesian product generally here, taking these terminal morphisms and pulling it back, and then we have this object. Okay, so and this is how we define basically the projection out of the product. So the projection of the right coordinate is taking bang A and pulling it back. This is this star along bang X. And so if we speak of these operations as I did here, to make this formal, you have to jump around a little bit between whatever categories you want to consider. You know, you have to jump around a little bit between the category and the slides category, and so technically it gets like a little bit confusing due to the notation and all the letters added. So for example, we have here not only this this operation that I use to define the projections, but of course this projection and this projection are projections out of this object, and you can do this with any objects, and if I would do this with other objects, then these projections would of course the particular projections that go out of the particular objects where I do the operation, right? So I could actually denote this projection left also by saying this is a projection left of x times x, and then I could add an infinite number of notations and it blows up. So this is just as a warning. If you want to write it down by something that is not just a diagram to characterize it, then you might have to check in which category you express the relation. But nonetheless, the diagram captures the relation well. And so now I want to talk about what goes on around this diagram. So okay, again, here's the terminal object a times x, and we want to eventually get at these function spaces, right? So in the case of set, we would be interested, for example, in the functions from x to y, which in the category of sets is like characterized by one set itself. And so this is one thing. And also I have this y lying around here. I have this y lying around here in the category, of course. I have this y times x as well. And so the final part that we need is adjoint functors. Many concepts in category theory generally are defined by saying, oh, here's a functor, I define this and that construction or this and that functor by demanding this left adjoint to this functor, or this is a right adjoint to this functor, and so on and so forth. The same thing happens here as well. So generally, if you have a functor f and you consider the errors from fa to y, then the adjoint to this f would be another functor that acts in another category, or acts in the opposite direction actually, such that this class of errors is equivalent to that class of errors. And you can look up in some book or the Wikipedia page to get the technicalities and see all the niceness conditions and all the results that you get and all the notions of equivalence there. But essentially it's flipping around between two functors with respect to two categories, going in two different directions. And what I've written down here is the main example, and that is also the important example for this video. If the functor f is just taking the product, the Cartesian product from the right with x, right? It maps a to a times x. Then the adjoint to that would be the functor mapping y to the function space y to the x, and that this adjunction is actually very constructive as well, as you know, at least for sets. The example that I give here is if you have some function of two variables a and x, and you map it to some function, in this case I choose a times sine of x, then you can take this function here and make a new function out of it, which is given like as follows. It takes an a and returns another function. So this is a function which returns a function which maps x to sine of x, where this is just currying, uncurrying. And other examples would be, in propositional logic, there's the rule, for example, if you have some propositions a, b, and c, then given a and given b implying c, this statement is equivalent to a implying given, like a implies given b, c is implied. So there's there's this like simple propositional logic rule where you can get rid of the conjunction, and that's also an instance, if you will, of this kind of form. Or the exponentiation rule of natural numbers would be one like 8 to the power of 3 times 5 is the same as 8 to the power of 3 to the power of 5. So the fact that you can get this 5 in and do multiplication instead of exponentiation inside of the exponent, this is exactly this rule in set, but expressed in terms of cardinalities of finite sets. Okay, so there is this notion that the space that we are after, this at least in set, the normal function space or f function space is given as a joint to the product, right? And we have just discussed characterizing the product in the category of theoretic terms, like pulling back this errors to the terminal object. And we're going to do the same thing here, and in the end, this way define the general dependent product, which by construction then, in the case of simple projection, reduces to the normal functions. Okay, so first, given functions. Okay, so we have seen that functions from a to y to the x are in bijections and to a times y, like functions from a times x to y. And so where we are going to start is on this side. So we start with a times x to the y. This is something we can build in a Cartesian closed category. This we translate now to the following. This in the same way that we did here, where I said, hey, I can add another x in the codomain, like I can do the product with the codomain. I can do this here as well, and this to get the normal function space back that we started with, we have to add this condition, right? This projection condition. And in this case, this can also be expressed here as this commuting triangle in this diagram. So AX is here. What we want is that we will take this space of functions here, right, from AX to YX, but we demand that the second component is actually fixed. And in terms of projections, that means that if you go from AX down to X over this this projection, the right projection, and if you go from here to this codomain space and then project out, then you if you have the same thing comes out here, then basically this the second component in terms of sets was left untouched. And now even if we don't speak of sets, and even if we don't think of the errors as functions, we take this rule, right, this computing triangle, and add it as a condition, and say we look now at the functions from here to here which fulfill the relation that this triangle is fulfilled. And this triangle, by the way, can also be expressed as just the existence of these functions in this slice category, because here we are over x, so this is an error in from ax into x, so this is an object in this slice category over x, and this as well, and this is basically this corresponds to a morphism in this category. And so by that logic, we see that this space of errors, this class of errors plus this condition, is also in correspondence with the functions, like the functions from here to here, are also functions in this last category, where these two projections are a projection here and projection here. So they have different codomain, they have different domain here, but my point is just that this line is the same as this line, it's just expressed in another category, in this last category. And we also have that this PR, like this projection R, like the way I introduced it, is this pullback of bang A along bang X, right? And now, if we look at the set theoretic case again for a second, then we had that, of course, in this category of sets, this object from X to Y is also inside of this category, and it can also be expressed in the slice category, namely in the slice category over this terminal object here. And so with this identification of a function with its domain, right, we have that A is identified with the bang A, and Y to the X is identified with bang Y to the X. And so since we are after this function space from A to X to the Y, this is in terms of sets. If we translate it, if we generalize that to whatever Cartesian closed category, then the relation that we have in set can it be expressed as this little bit strange looking line. So this is the slice category error class with this projection expressed as this pullback to this projection is, at least in the category of sets where we know it, in projection with this class of errors in this last category over the terminal object. Okay, and now in the last step, what we do here to define the dependent product is we just say, hey, okay, we have now basically isolated in this expression this pi r, right? So this is this pi r that we have used here for the sets, and we just say now, okay, if we consider a general p, so like this p, for example, this is a general p from some space, from some object A to some object X, and say, hey, what is actually the adjoint to this pullback of bang X? So this observation, we take this in as a functor, which if you like look into it, you can, like, since this works over all these objects, this pulling back in the Cartesian closed category, this is a functor, and now you say just, okay, I define my dependent product as the adjoint of that, similar to that, like is a generalization of this simple adjoint, and say, oh, I pass from this bang X pullback to this functor capital pi of bang X on this object B, and this way I characterize this new product kind of space, this section space. If you could follow the explanation, then it's clear that in the set theoretical case, this leads exactly to the function space, but we can ask for the existence of this product also for any general p, because this is just errors. This p is just an arrow into X, or an object in the slice category over X, and so we have this general definition, and that's how it's generally set up. So we, like, if we start with that, we can talk about these things in Cartesian closed categories. So this will exist, and we are away from anything that has anything to do with sets. We just say, oh, what is the adjoint of the pullback along the one terminal arrow with respect to another in the slice category. All these things exist, and so this we can ask after this object as well. Okay, and the last thing I can say is, I mean, you can also abstract away these bangs and take more general errors. Then you can speak about the dependent product with respect to a general error. In the same way, you can speak about this pullback with respect to general alpha and beta. But that's a detail. I mean, the dependent product that we're usually after, and especially if you think of type theory or the semantics of it look like that. Okay, so I hope that was sort of clear, or at least it made you interested in this kind of concepts. You can ask about it in the comments, of course, and I'm sorry if the audio was bad. I will find it out in a second. Take care.